Hi, this is Mr. Smith, and I just wanted to talk really quickly about incorporating rotational kinetic energy into our ideas about conservation of energy. And so I'm just going to draw a hoop at the top of this ramp, and let's say that its velocity is 0 meters per second. So it's not moving at the top of the ramp. And let's say at the bottom of the ramp, it is moving. It has some velocity. Its center of mass is moving translationally, and it's rotating around and rolling without slipping at the bottom of that ramp. And we'll call this point A at the top, and we'll call this point B at the bottom. And very similar to what we used to do with energy problems like this is we would make a little kind of table and we draw a circle, and that would be our system, and our system would be this disk over here and the Earth. Okay, and the possible types of energy that we're dealing with at point A would be kinetic energy or rotational kinetic energy or gravitational potential energy. We don't have any springs, we don't have any elastic energy to deal with. And at point A, it is not moving, so there is no rotational kinetic energy and there's no translational kinetic energy. It would all be just gravitational potential energy at point A at the top of that ramp. And so we could say our energy to start with would just be mass times gravity times height. At point B, okay, we'll say this thing is all the way down to the ground. And so we do have some rotational and translational kinetic energy, but we won't have any gravitational potential energy. Okay, and so we'll draw in some translational kinetic energy and we'll draw in some rotational kinetic energy. Okay, and we could figure out the actual ratio of those things depending on the shape of the object. But the important part here is that our kinetic energy would be 1/2 mv squared, and our rotational kinetic energy would be 1/2 I omega squared. And so that would be the equation we would want to make for this situation. It's going to be pretty common that we will want to substitute in for this omega. Remember that, or angular velocity, that our translational velocity will equal our angular velocity times the radius. So our angular velocity will equal v over r. And there's a lot of times we'll take that and just put it in for that angular velocity. This is a r over here. It's also pretty common that we'll get an equation for this rotational inertia. So maybe if it's a disk, I think it's something like 1/2 mr squared. And so we could plug that in for that I value. But the big idea is we make these equations just like we did before, use the same strategies to think about them and implement conservation of energy.